Hello, my name is Dr. Ashok Gadgil. I'm a professor of environmental engineering at UC Berkeley and a faculty senior scientist at Lawrence Berkeley National Lab. I'm going to speak to you today about technology to support human rights to safe drinking water, stop arsenic poisoning, also give you an update on what I've been doing since my team and I won the IPW prize several years ago. I start by giving a land acknowledgement that UC Berkeley is located on land that traditionally belonged to Native American tribes, Ohlone tribes, and we all benefit from occupation of those lands and use of those lands, and we recognize the history of the land on which we work. And I gratefully thank for support numerous institutions and donors and advisors and well-wishers and friends of this effort, which has extended for 15 years now. I want to give a little bit of background that there was a successful campaign to switch people from surface water to groundwater, Bangladesh and India in 1980s. And in 1990s, arsenic was discovered in the hand pumps, which led to arsenicosis, and arsenicosis has these horrific effects. The photograph primarily showing ulceration of the hands, including for the child in the lower panel, amputation of fingers and hands, internal cancers, and so on. Access to drinking water is recognized by the UN General as a fundamental human right, and the Sustainable Development Goal number 6 supports clean water and sanitation for all. Even then, hundreds of millions of poor rural people have no other water to drink than groundwater contaminated with arsenic. Arsenic is everywhere, but the problem is most severe in Bangladesh and nearby parts of India. Chronic exposure to arsenic causes numerous horrible side effects or health effects, which are listed in the slide. But we are going to, in the year 2000, WHO called this the largest mass poisoning in the recorded history. Let us now look at only internal cancers and ask the question that if 100,000 people drink water with a given carcinogen over their lifetime, how many excess internal cancers can be expected? And the answer is shown in this graph, where the vertical axis represents excess internal cancers over a lifetime, and the horizontal axis shows different carcinogens which are allowed in water. So the serious one, the most serious one, is ethylene dibromide, which at its MCL over a lifetime causes 12 excess internal cancers. But notice that we exclude in this graph arsenic. What happens if we add arsenic to this graph? Watch the vertical axis now. The excess risk from drinking arsenic-bearing water at its MCL, which is 10 parts per billion, is about 740 compared to all the other risks which are now showing as little blips on the x-axis. That's how bad arsenic is, even at its MCL. But in fact, arsenic concentration tens or hundreds of times higher is detected in water that people routinely drink. And no surprise that people are very, very sick with horrible effects. Here are a number of examples of arsenic removal units or ARUs placed in rural India. And a student of economics was studying how long do they last, how do they function in the world. And they are all based on decent technology that works in the laboratory. This is what happens in the field. 95% of them fail within 1 year. This is a PhD dissertation of Dr. Abhijit Das, who is now a professor of economics. And the reason they fail is not because of the technology by itself, but because the technology was located in the social context without paying attention to financial viability, without social integration, and without sustainability. So this is what we set out to repair, everything that can be integrated in society and can be affordable. That technology is called ECAR. It was designed to fit within a scalable and sustainable technology system. So how does it work? In water, we have these two steel plates and an external battery, which causes one of the steel plates to dissolve in water, which produces Fe2, and then all of arsenic 3 is oxidized to arsenic 5, which then attaches to Fe3 ferric hydroxides. And arsenic also gets removed, but so does phosphates and silicates. They all precipitate down into the water as coagulate. And then we actually get what is called LD, or zero liquid discharge. I want to start with a quote, a famous quote. The best way to have a good idea is to have lots of ideas. So don't be afraid if your idea is going to fail, because you must think that is worth trying. And if it's worth trying, then it's fine. If it fails, you have more ideas to try. So in 2005, when we started, we didn't know if we'll succeed, but we took a risk. And we were just trying to see if we can remove arsenic. And we could remove arsenic 5 out of pure DI, that's deionized water. By 2010, we had progressed from that little glass beaker on the left-hand side to a big white reactor, 100-liter reactor that you see standing on the ground on the right-hand panel. From there, we went to 600 liters. We went to 600 liters in the field in India, and then to 2,800 liters. We also paid close attention to community engagement and buy-in. In parallel, we pursued 3 tracks: basic science, fundamental science, technology, and reach out to people, and a two-way communication with the community. So not only lecturing them, but listening to them and asking them what do they care about, and answering their questions respectfully and with honoring the fact that they have to live with the technology. And we must respectfully and humbly go there, not as arrogant white-collar scientists being in the village. So this is a process flow schematics, and this is what the huge tanks look like. This is 2015, about a couple of years after we won the PSIPW prize. And the iron plates in the reactor is what is going to dissolve in the water. Here is a team that I'm working with, a small part of the team. Most of them are professors in India. Some of them are staff, research staff in India, and the reactors are in the background. This is how the reactor performs. It has been performing like that for now 5 years, since 2016 beginning until now. Initial arsenic is 252 parts per billion, and final delivered arsenic is less than 3 parts per billion. And here are school children who get water for free in exchange for giving us opportunity to use one of their classrooms to build a plant. But the excess water is sold to thousands of people in the community. That pays for the operation and maintenance and salaries operated by the private sector company, which received all the manuals, documents, and their licensee. Their name is LivePure. They operate the plant now. So what has happened to the cancer risk? The cancer risk was not 740. Now it has 18,000 if people drank water from the groundwater well. But with the plant operating, there is an 80% reduction, and of safe water sells to the community at 1 US cent per liter, meeting and exceeding all WHO and US EPA standards for biological and chemical contaminants of all kinds. It's a financially viable plant. The estimated return on investment is about 30%. The technology approved by the Indian government is 2018. But we have continued to develop the technology for poor rural communities, even in the first world, because they also don't have a right solution. That solution we invented is called air diffusion cathode assisted electrocoagulation, or iron EC or ASAI. In this case, instead of an iron cathode, we have an air diffusion cathode. As you can see, it allows oxygen to go through a porous wall, and it produces hydrogen peroxide inside. And that makes it 10,000 times faster than the standard e-car that we used in India. And that also makes it compact and produces lots more arsenic-free water at a much smaller volume and therefore much smaller construction cost. We have actually designed this. We have actually built it. We test data. Note that the x-axis is the experiment cycle. We show you 3 experiments each. On the y-axis is a residual arsenic. It shows that if we go fast with e-car, we still get about 600 ppb arsenic. But with ASAI, we get less than 10 ppb arsenic. Another way to put it is, what e-car will take 3 hours and 20 seconds to do on the left-hand side panel, duration box, ASAI can do the same, deliver the same quality of arsenic removal in just 30 seconds. So we are funded by the state of California to build and test this system in the rural California community, and that's what we are working on now. It remains a zero liquid discharge technology so that there is no water molecules that are wasted. All the water that comes in shows up in the final finished water stream. That's where I would like to stop. Here is my email address, and at the bottom of the slide is the website of my research group where you can find more information. Thank you very much. It has been a pleasure.